In this last video, we're in section 11.4, and I wanted to talk about the concept of epidemiology. So summarize the goals of epidemiology and differentiate it from traditional medical practice. Epidemiology is the study of the frequency and distribution of disease and other health-related factors in defined populations. This includes all disease, not just infectious disease. If you wanted to become an epidemiologist, you'd probably need a master's degree or higher in public health or epidemiology. So you could get a nursing degree and then get a master's degree in public health or epidemiology and be an epidemiologist. So what does an epidemiologist do? They identify causative agents, what's causing the problem, whether it's an infectious disease or diabetes, a non-infectious disease. They can track behaviors and diseases. They do surveillance, which is keeping track of trends in non-emergency times. So they're checking for the frequency of different conditions, even when there's not, like a pandemic or something. So all the time. So you can kind of have a baseline of what's normal. Keeping health-related data. And so a lot of this, you can see a lot of this will relate to mathematics. So you better be interested in math and statistics and all, and mapping and all that kind of stuff if you want to be an epidemiologist. But I wanted to mention, I mentioned it earlier in the last video about the Centers for Disease Control and Prevention. This is the main public health organization in the United States. Its headquarters are in Atlanta, Georgia. And the CDC has a wonderful website. It's the keeper of our primary epidemiological information in this country. Explain what is meant by a disease being notifiable or reportable, and provide examples. So I've typically used that term notifiable disease, but you also hear it called reportable diseases. And so it turns out that there are laws about public health, and these are public health laws and kind of come through the CDC. And what a notifiable disease is, it's one that's required by law to be reported to government public health agencies. So if you look at this, and you can't see it that well in this video, I'm sure, but it's table 11.9 from your textbook. And it has a list of this is from 2019, the 2019 nationally notifiable infectious diseases. What am I seeing? Botulism, West Nile virus disease, Powassan virus disease. What else? Some of these we know of. Cholera, coccidiomycosis, diphtheria, giardia, salmonella, plague. There's all sorts of diseases that when somebody shows up in a hospital in Corning, New York, they have to report that there was an incident of this disease to the county public health agency, and that county public health agency probably rolls into a state agency, which ultimately rolls into the CDC. So there are statistics on all of these diseases about what's going on at all the time. So, and this list of the nationally notifiable diseases can change. I mean, there's some diseases that have been on here for a really long time. But Zika virus, is a relatively new virus. And so that was one that was added later. So this can change. Here's a couple epidemiological terms. Explain what the epidemiological terms reproductive rate, or you might hear this called basic reproductive rate, and it's R subscript 0, or you might hear that called R naught. But I just usually call it the basic reproductive rate, and the case fertility rate, CFR, and why are they important? So the basic reproductive rate is a measurement of communicability of a pathogen. How communicable is a pathogen? How easily is a pathogen spread from one person to another? So it's a number that tells how many susceptible people on average one infected individual will spread the infection to. So if that doesn't sound too clear right now, I'm going to show you something in the next slide that will hopefully clear that up. Another important epidemiological term is CFR, case fatality rate. Now that one's easier to understand. For people who go untreated, this is the percent of infected people on average who will die as a result of the infection. I think I heard the CFR for C. diff might be around 60%. So fortunately, most people that get C. diff get some kind of treatment, and it doesn't have a death rate that high. But the case fatality rate is going to be the percent of infected people who on average die as a result of infection if they are untreated. So let's look at, this is in your textbook, and I think this is kind of interesting to look at. This is the deadliness, the case fatality rate, and here's the communicability, the basic reproductive rate. And so the most deadly diseases are going to be at the top. And you can see like rabies and HIV, if left untreated, are both very deadly. We've got tuberculosis, Ebola plague, and some of these other diseases, although we know a lot about them, aren't quite as deadly, but 24% death rate is still pretty high. And for something like smallpox, it doesn't have any treatment, so that's pretty bad. But you can see kind of how that goes. And then the communicability measurement, the basic reproductive rate, look at that. The most communicable, most that are easily transferred from person to person, look what's up there. Measles, malaria, mumps, rotavirus, pertussis, which is whooping cough. Some of these we have vaccines for, and we're insistent upon people getting vaccinated for measles, mumps, and pertussis, because these diseases are easily spread from person to person. And they might not be very deadly. In fact, you know, they're down here. These aren't diseases that are going to kill you. But if a lot of people get sick, and even it has a minor rate of death, case fatality rate, you could end up killing a lot of people. Here we have chickenpox are very communicable. Some of the less moving down, we have smallpox, polio. But again, these are still going to be able to be transferred from patient to patient. So my next learning outcome is explain how the basic reproductive rate can be used to help calculate herd immunity. And so remember the basic reproductive rate, is how contagious something is. And so before we talk about this, I need to define herd immunity. And I think a lot of you understand this because we've talked about this a lot during COVID and the pandemic and how many people need to get vaccinated. But I'm going to go through the concept. This is a picture. It's not in your book. In fact, this concept is not touched in your book, but I think it's really important. And this picture you can find on the internet. Just Google herd immunity and look for images and you can find this. So what we mean by herd immunity, it's the characteristic of a population that has a high enough percent of individuals who are immune to an infection, they've been vaccinated, to provide protection to those who are not immune from being infected. So let me explain what that means by looking at these pictures. First, we have these blue people that are not immunized but still healthy, okay? And so they're showing you that we've got all these healthy people. These two red folks show up, and these are not immunized, and they're sick and contagious. And what's going to happen is these sick and contagious people are going to spread their infection to most of these people because these people are not protected against that disease. They don't have antibodies against it. So they're showing you here that most people in this population will become sick. And that's what was happening at the beginning of the COVID-19 epidemic, that people, we have one person that arrives that's sick and they spread it to lots of people because none of us were protected against that infection. Now, another scenario is we still have all these blue folks. Most people are still not immunized but healthy. But we have a few people in the population, these yellow people, that are immunized and healthy. So they're not going to get the disease, or they're not likely to get the disease. And these same two sick people show up. But what's going to happen is most of these people are still going to get sick. The people that have been vaccinated, most of them are going to be in good shape. They're not going to get sick. But we still have a lot of people that are susceptible to that disease. So that infection is still going to spread. Now, in a population where most people are vaccinated, or a high percentage of people are vaccinated, so all these yellow people are people that are vaccinated, we have a few people that aren't vaccinated, and they're susceptible to a disease. Now, in an ideal situation, these few people who are not vaccinated are newborn babies. They're people that have an immune deficiency and can't be vaccinated, or they can't create an immune response. They might be people undergoing cancer treatment, or they might be getting organ transplants where their immune system is depressed. And so they're not able to mount an immune response against this pathogen. So these are people that we're trying to protect. So these sick people show up, and what's going to happen is people aren't going to acquire that disease because they're vaccinated. And they're not going to spread that pathogen to other people. And so even these people that aren't vaccinated, most of them will be protected because they're surrounded by people who are not going to get the disease, and they're not going to spread that disease to them. This is the concept of herd immunity. With herd immunity, we have enough people in the population who are vaccinated against a disease that it enables them to protect the weaker individuals in the population. Okay? Herd immunity, it will protect those people that can't be vaccinated. So let's go back to our learning outcome. Our learning outcome said, is asking, how can the basic reproductive number be used to calculate herd immunity? And there's a formula, but you don't have to memorize the formula. But what it's showing you here is that mumps, remember we said mumps and measles? Oh, wait, we said measles and pertussis are really easily transferred. They have a high basic reproductive number. So look at this. If somebody gets measles, they're likely to transfer this infection to 12 to 18 people. The higher the RO, the higher you need your herd immunity to be. So because you can transfer measles to a lot of people, you need to have, here they say 83 to 94% of people vaccinated against measles to protect the weak individuals in the population, the people who cannot get vaccinated. Now, if we look at something that has a lower basic reproductive number, like mumps, if somebody gets mumps, they're saying about 4 to 7 people will become sick from this person. You don't need quite as many people vaccinated, 75 to 86% vaccination rate, in order to protect your population, in order to get herd immunity. So here it says, the more infectious the organism, the higher the basic reproduction number. And so the higher you need your higher vaccination rate to have herd immunity. So with influenza, the basic reproduction can vary with the strain. So depending on the strain of influenza, we need 13% to 100% of people vaccinated to protect the weaker individuals. So that's a huge range. So the goal generally is just try to get as many vaccinated as possible. The other one that we have here is, I was trying to find some numbers for SARS-CoV-2, for the pathogen that causes COVID-19. And originally it was estimated to be the basic reproductive number would be 2 to 3. So if one person got positive for COVID, they would transfer it to 2 to 3 other people. And if you do the calculation, that would make herd immunity about 60%. But that's in kind of the general population. In some populations, it's higher. So in a population of like a nursing home where most people are older, you need a higher vaccination rate. Now, the other thing that happened is that the original strain of COVID-19 had a basic reproductive rate of 2, basic reproductive number of 2, but we got all these new strains coming up. And so that changed it. And so here was one with 5. And then they even said the Omicron might have been as high as 9. So as the strains of the virus changed, our need for herd immunity changed. And sometimes it got higher. So typically what you do is you shoot for about 80 to 90% vaccination rate to have effective herd immunity. The last thing I wanted to talk about in terms of epidemiology is just some vocabulary. So I wanted to distinguish between endemic, sporadic, epidemic, and pandemic disease, and what factors are related to pandemic disease. So endemic disease, just vocabulary word. It means a disease that exhibits relatively stable frequency over time in a geographic locale. So I would say HIV is endemic to upstate New York. Lyme disease is endemic. Influenza is endemic. Syphilis, gonorrhea. There's all sorts of diseases that are they're found in upstate New York. We have a relatively stable frequency. And so we would say that disease is endemic. A disease is not endemic to upstate New York would be Ebola or yellow fever or Zika virus. Like lots of things aren't endemic to upstate New York. A sporadic disease is one that has occasional cases at irregular intervals. So tetanus. We don't have tetanus all the time, but somebody might get tetanus. We don't have diphtheria all the time, but there might be a case of diphtheria. Botulism. Last time I looked at the botulism statistics, so far in the U.S. this year, there have been 8 cases of botulism. So that would be a sporadic disease, one that occurs occasionally, but it's not there all the time, not endemic. These would be very low numbers. An epidemic disease is when the number of cases exceed what is expected from an endemic or a sporadic disease. It's going to be a disease that it's going to be above the typical endemic or sporadic numbers. And we're going to look at some graphs in the next slide on epidemic diseases. The last vocabulary word I wanted to talk about was pandemic disease. And so that would be an epidemic that spreads across continents. And we're all familiar with that with our coronavirus epidemic that we're just passing by right now. This is a picture from your book and figure 1110A. And what it's showing you is this is a graph, and this is something an epidemiologist would put together. In fact, this came from the CDC. And it's a graph of an epidemic. And so here are, in a certain area, I don't know where this data comes from, in what geographic area, but what they're showing you is they went from February to July in this area. And here's like the 3-year kind of average, this black line of salmonella food poisoning. And what you can see is you get in this period of time, there's some blips on the graph here where there's an increase. There's some epidemics. And what they trace this to, because they do this surveillance, like how much salmonella is around normally, when you see a increase in numbers like this, and it's happening over and over again, it makes you say, this isn't just like one person's house that had a salmonella outbreak. And so they start looking at where is this coming from. And it turned out in this particular data, there was a chicken processing plant that put some chicken on the market that had salmonella on it. And so people were eating it, maybe it showed up at certain times in the markets and had large numbers of this salmonella food poisoning. And because these epidemics were occurring, it allowed the public health department to trace it down to a particular chicken processing plant. So collecting data like this can stop these epidemics. Here's another one from your book, figure 1110B. And it's another epidemic, but it kind of has a different pattern. This goes across a year from October to October, and it shows you the influenza epidemic. And this is really common in many places around the world, that we have this, we don't have a lot of flu in October, but look at this. Once the winter months come along, we've got this, what we call a seasonal flu epidemic, and it dies down. And then in the summer months, we don't have very much flu. And so again, we can see this pattern year after year by collecting these data on epidemics. In the last slide, I just want to mention the concept of pandemic again. And remember, pandemic was a worldwide epidemic. And one of the things I would like you to notice about pandemics is these are typically caused by pathogens to which we have no natural immunity. They're usually new pathogens. So these are things that we don't have a vaccine for, that haven't been around before, because most people are susceptible to it, which allows it to spread throughout the world. And it's just kind of fun to look at some of these numbers. You can see here some of the more recent pandemics. The Spanish flu pandemic, over 50 million people got that. The numbers are kind of maybe not real accurate, because we didn't keep statistics on things like this in those days as well as we do today. But you can see what the Asian flu, 2 million in 1957, HIV pandemic, over 30 million people. This is funny because here it says 2019, there's about 3,000. Well, this was put out in 2020. So I went and got a little more recent data. And in 2020, by 2022, by the end of 2022, there were 6.3 million deaths from this. So not quite as bad as the Spanish flu, but definitely bad compared to a lot of these other pandemics. So remember, a pandemic typically will occur when it's a pathogen to which most people do not have natural immunity. We don't have vaccines for, and people haven't been exposed to it before. On that note, I'm going to call this section to an end.